So again, sorry, I did that without turning this on. After doing probabilities, now we're going to go distribution functions. Today we're covering what's called the binomial distribution and the geometric distribution. On Monday, it will be the hypergeometric and then the Poisson for all my French speakers in the room. What is Poisson? P-O-I-S-S-O-N? Fish, that's right, good. Don't know your French? Come on now. It is. All right, so this is what you started with. You found the probabilities of all the sums, which you started out by saying, okay, there's a sum of 2, a sum of 3, a sum of 4, all the way up to a sum of 12, and then you figured out the probabilities of each of those happening. All right, so if you're watching this online and you're like, I wasn't in class, sit down with this right now, and you're going to go through and try to find the probability of all them happening. Probability, of course, is defined as how many ways can it happen out of all possible outcomes. So you're thinking, how many ways can I get a 2 with 2 dice? I add them up, find the sum. But we did it, and we found this. That's what your distribution looked like. Now, some of you didn't actually draw it like this, but you had like this, but you had a triangular-looking piece. So this would be the probability distribution function for the sum of 2 dice. So that's what we're looking at right there. So as you're doing problems on the Check Your Understanding from your book, and it's talking about the probability distribution function, it says make one, this is what they're talking about. You'd make a little, and in this case, it's a bar graph, not a histogram, because you can't get, you'll either have a 2, a 3, or a 4, but you can't be between a 2 and a 3. So there has to be a gap right there. You're either a 2 or a 3, but you can't be both. In a histogram, those lines would overlap because you could actually be here or there, but you have to happen to just be right on the boundary. But the expected value, which is also called the mean, is, there's the function for it, which is what we've already covered when we talked about finding the average of a histogram. The average of a histogram, so if you're given a histogram and said, use this histogram to estimate the average, you took the midpoint of the histogram and then you multiplied it by the count. Midpoint times the count, midpoint times the count. In a probability distribution, we're going to go midpoint times a probability, midpoint times a probability. So as you did this, you did midpoint 2 times its probability was 1/36, plus midpoint 3, because this one's not listed there, but that's a 3. And that was times 2/36, plus 7, which was 6/36, plus 8, and then it started going back down again, 5/36, plus 12 times 1/36. That's a 3, but there's a 36 down there. Pretend. I know it's messy, but that's why I get to talk and explain it. So that's a 36. So that is finding the expected value of a probability distribution function. And you did that, and you found that the expected value of x, which in our case, x is the sum of 2 dice. If you did this, it was 7. Some of you might have looked at this and said, well, of course it's going to be 7, because 7's in the middle, or 7's the highest one. The only reason why it's 7 and not some other number is because this is exactly symmetric. If it's not exactly symmetric, it will not be the middle, the highest probability value of actually happening. All right. And what does that mean? That means on any given roll of the die, I would expect that the sum of the 2 dice will be, on average, if I do it a whole bunch of times, it'll average out to 7. So after you've contemplated this for a while, we'll come back, but see if you can figure out what that means. So each time you play, you guess, they draw and look at the card. Now theoretically, I would have shown him this card, but I didn't want him to see that he lost on his first guess. Tried to make it feel like it was going to, like a game last a little longer. No, he did not get any of them right. So if you do this, you draw the card, you guess the suit, and then they look and they say, oh, if you get all 4 of them right, all 4 guesses, you win $256. But again, after every draw, the card is put back in the deck. See if you can figure that out. I hear some good conversation happening. Let's consider this. Remember our discussion on probability. If I want to get all 4 of my guesses right, if I want to guess, I'll do a plus. Correct, 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 correct. Is this So again, we're thinking the 2 rules of probability from chapter 3. Is this an and situation or is it an or situation? Don't answer out loud, but you're thinking, do I want to get the correct suit guessed and the correct suit guessed and the correct suit and the correct suit? Or do I want to do the correct suit or the correct suit or the correct suit or the correct suit? It's an and situation. So in terms of probability, I want to be the probability of right and right and right and right. Are these events independent? Does knowing the outcome of the first one have any effect on the probability of getting the right outcome on the second one? No, it does not, because we put the card back and we reshuffle it. So since we're doing sampling with replacement, they're independent. And with independent events, that means I want to find the probability of being correct times the probability of being correct times the probability of being correct times the probability of being correct. What is the probability of being correct? 1/4. How many suits are there? There's 4 suits in a standard deck of cards: spades, clubs, diamonds, hearts. There's an equal number of them. So if I'm going to guess the correct suit, I had a 1 in 4 chance of guessing the first one the right. Then I have a 1 in 4 chance of guessing the second one. Then a 1 in 4 chance of guessing the third one, and then and I multiply those, and I find that the probability that I get 4, so I get probably of all 4 suits guessed correctly, is 1 out of 256, right? 16 squared, 256. So then we're going to do expected value. Expected value of x is equal to the sum of each x times the probability of it happening. So when I have x sub I, I'm just meaning the first one, the second one, the third one, so the list of all the x's. So what is the first possible outcome that I have in this scenario? You play the game, you're going to either what? Win or lose. So I'm going to win. If I win, how much do I earn? $256. So that's my x. If I lose, how much do I lose? $1. But I'm going to write it as -1 because you lost it. Got to have positives and negatives when you play this kind of game. What's the probability that I win? 1 out of 256. What is the probability that I lose? 255 out of 256. The expected value is the sum of each outcome times its probability. Outcome times the probability. So if I multiply those, I get 1. If I multiply these, I get -255 over 256. And then after I do that, then I sum them up. That's capital sigma. So I'm going to add them all up. So I add up 1 plus -255 over 256, and I get, how are my fractions? 1 over 256, positive or negative? Positive. So in the long run, I am going to come out 1 over 256 dollars if I play it a long time. Or I should say, realistically, on every single play, I'm expecting to play and get 1 out of $256. Which means, in the long run, I will make money. Just barely. Okay? Another way to think about this is this 256 winnings is also 257. If you think about it, you paid $1 to play, but we counted for it here. So it's always trying to keep track of what's going on. So if you win, you get your $1 back plus 256. So did I win 257? No, but also yes. But either way, so in the long run, you are winning just ever so slightly. This is how casinos make a lot of money on stupid people, because they know that you're going to keep playing with this off chance that you might win, because many of their things are like this. -1 out of 256. So you're like losing, on average, a half a cent per play. Well, that's not so bad, but people play a lot. And they think they're about to get lucky, and then they're not, because luck is a myth. All right. So that's how things work. So in terms of figuring out expected value, this is how we're going to do it for this type of a distribution. So this type of a distribution, obviously not symmetric like the one was that we did with the dice. So this is just our standard probability distribution. It doesn't have a special name because it doesn't have special scenarios. But this one does. Oh, and here, sorry. We'll do this. So we did the probability, or the expected value and the average. Expected value is the same as the average. If you have to calculate the standard deviation, this is how you would do it. We're not going to. We have technology to do that for us. But the standard deviation is found by, well, I take each outcome, subtract the mean from it, square it, and then multiply by the probability. And this is squared, which I can't remember if I've talked about in here. So this is the variance. Lowercase sigma squared is variance. So the variance is sigma squared. Lowercase sigma all by itself is the standard deviation. It's just that one is called one thing, the other is called the other thing. If you ever decide to go in and do any kind of pursuit in statistics, you're going to spend a lot more time with the variances because it's easier to work with because it's not being squared or square rooted. But in this case, and in our class, we're going to spend almost all of our time talking about the standard deviation instead. So the first one's the binomial distribution. So there's 4 conditions for a binomial distribution to be happening. A binomial distribution has 2 outcomes and 2 outcomes only. There's only 2 outcomes. Every single event or trial or play of the game or whatever has to be independent of all previous ones. So like we did with the cards, every shuffle, we put the card back in, which made every event going on independent. And that means when they're independent, that the probability of success stays constant. We're going to have n number of trials, and we're going to find r number of successes. You can look up a binomial distribution anywhere, and it's going to give you these 4 conditions. If it doesn't meet these 4 conditions, I can't use the binomial formula, which will be coming up on a slide right there. You're looking at that thing. What is that formula? NCR is combinations. If you've done combinations in the past, you're like, oh, or you're going, oh. Not many people are really excited about combinations, but this right here is a formula, and it's n factorial divided by n minus r in parentheses factorial times r factorial. It is basically saying if I have n trials, this number, this NCR number, this is how many ways it could happen. So if I have 4 things and I want to find out how many ways can I have 3 successes, well, you think of 4 things, you're like, okay, well, the first, second, and third, that's one way. First, second, and fourth, that's another way. Second, third, and fourth, that's a third way. So it ended up being 3. Factorial, so if I were to do this with my example that I just gave you, so if I had it 4 and 3, I'd have 4 factorial divided by 4 minus 3 factorial times 3 factorial. Factorial means 4 times 3 times 2 times 1. I'm not going to write the 1 because times 1 is just redundant. 4 minus 3 is 1, that's in parentheses, times 3 factorial, which is 3 times 2. What happens? The 3 times 2 and the 3 times 2, and I find out that there's 4 ways. So if I have 4 items, there are 4 ways to make 3 groupings. How's that going to help us? You'll see when I get to a little bit of a probability scenario here in a minute. So that's this number. This is P, probability of success. R is how many successes. 1 minus P, I'll oftentimes call Q. That's supposed to be a pencil. I'll oftentimes call it Q. Probability of success is P. Probability of failure is Q. Success and failure are determined based on the scenario. So don't get offended if we're talking about certain things happening, like a mortality rate. And so the success is someone dying. I'm not saying that like emotionally that should be a success. But in terms of how the statements are defined, we'll determine which one's a success, which one's a failure. All right, so And then it is whatever's remaining. So success times how many successes I want, failure times the rest of them. Because in total outcomes, this is how we write it. This is saying I have a variable x that follows a binomial distribution with n number of trials, and p is the probability of success. The average of a binomial is n times p. Oop, and something didn't come over in the standard deviation of a binomial distribution is the square root of n times p times q. So again, just knowing the formulas is one thing. We're going to show how to use them here in just a minute, because formulas you can find anywhere. So I'm going to go on to the next slide. Steph Curry. I'm not a basketball fan. Some of you are like, what? How can you not be a basketball fan? I'm not. I really don't like it. I'll play it really poorly. Really, really poorly. Because I grew up as a wrestler, and so I play basketball like I wrestle. So I've broken other people's ribs. I've sent guys to the hospital. That's how I play basketball. And I win. Not by their rules, but by mine. All right? So I'm a terrible shot, too. But in 2023, Steph Curry had a 92.9% free throw completion percentage. So he was the top in 2023. Here's a binomial situation, sort of. One, is there only two outcomes? Yes, he either misses or he makes it. Are there set number of trials? Yes, he's going to do 12 free throws, so that's my n. Am I looking for a certain number of successes? Yes, in this one, my successes is 10. Do I have a set probability of success? Yes, my probability of success is 999. Come on, erase. There we go. 929. My Q, probability of failure, is 0.071. Ran out of room on my slide here. Oh, didn't want to do that. It's 0.71. Just got to make them smaller. 0.71. But the one condition that this does not allow us to have happen is independent. Because if you've ever played a game, a sport, and anything, where it involves your skill, if you make one, does that influence the likelihood that you'll make the next one? Oftentimes, yes. All right, so every individual shot typically is not independent of every previous shot. However, for the sake of argument, so we can do this problem in class, let's just assume that every shot he takes is independent of all previous shots. Right? So like Men in Black, a little mind wipe. He doesn't remember if he made the last one or not, just goes up to the line completely unaltered, takes his next shot. So if this is the case, this would follow a binomial distribution, and so this is what I would find. I am going to use proper notation, so I'd say the probability that x equals 10, because it says exactly 10, with that formula would be 12c10 times 0.929 to the 10th power times 0.071 to the 2 power. Again, with that previous formula, number of trials, number of successes, probability of success to the success power, I want 10 successes, failure probability to the failure power. So in 12 shots, I want 10 successes, 2 failures. I don't care what order they happen, but that's how I want to do it. And then I need to turn to technology and have something, either a graphing calculator, or you can actually find these online. If you search for a combination calculator, it'll show right up on your Google search, and it will say things like, mine just pulled up right here, N objects, 12, R successes, 10, calculate. And so this number right here is 66, which means if I were to do this, there are 66 different ways that he could shoot 12 shots and make 10 of them. It's going to be virtually impossible for you to sit down and crank through and try to count them all like we did when we did the probabilities of the sums of two numbers. but it's the same idea. All right, so you take that number times this, which you'll do in a calculator, times that, which you'll do in a calculator. And if you want, you can even go online if you don't have a graphing calculator and look up a binomial distribution calculator. And if you do that, the first one that pops up for me is from the University of Iowa, and it asks me for n. N again is 12. This time it asks for x, not r, but that's 10. And my probability of success is 0.929. Done. And it calculates it out. And my answer to this is 0.1593. There's a 15.93% chance that he makes exactly 10 shots. Next step, how would we find the probability that he scores or he gets at least 10? So at least 10 means probability that x is greater than or equal to 10. That's at least. So that means I would have to find the probability that x equals 10 plus the probability that x equals 11 plus the probability that x equals 12. You would do it 3 times, then add them up. I'm not going to do it in class because, again, this ends up being, once you figure out what the parts and pieces are, we've determined, hey, the conditions for a binomial are met. I'm going to use a binomial. My n is this, my p is this, my r is this, my q is this. I plug it into a formula so that I can see that you know which formula you're using. At that point, you just go to technology and let the technology do the walking. Let it do the calculations. All right? Do not try to do this by hand. It's going to take you a long time. But once you set it up, like I did there at the bottom, down here, I'll see, they know what they're doing. They've gone through, they've confirmed the conditions for it to be a binomial. They showed the binomial formula with at least one of the numbers plugged in. That's all I need to see. I want to know that you're picking the right formula based on the right reasons, you know the right numbers to put in, and then we use technology to get ourselves to a final answer. Fewer than 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Is that too much work? Yes, but we just did more than 10 or 10 or more. So if I know 10 or more, I can go 1 minus that to find what's just under 10. And then lastly, the mean and standard deviation. The mean is n times p, which is 12 times 0.929, which is 11 point something. So that would mean, again, interpreting this in context. If I were to take any set of 12 shots that Steph Curry attempted, I would expect, on average, over all of those different sets of 11 shots, that he would make 11 point whatever that number is. Again, I don't know the number off the top of my head. I don't do that kind of math in my head. 11 point what? 148. So on average, he would expect to make approximately 11.148 shots out of 12. Standard deviation, I take n times p times q. 12 times 0.929 times 0.071. Multiply that, take the square root. That's the standard deviation. That's the binomial. This one then is what's called a geometric. So geometric is similar to a binomial, but what differs is instead of having a set number of trials, we're going to do something until we have a success. So here's an example. When you roll 2 dice and you find the sum, you win if you roll a 7 or 11. You keep on rolling until you win the game. What's the probability of winning? 7 or 11? Well, 7, we did that earlier. There's 6 ways to get a 7. How many ways can we get 11? 2 ways. So there are 8 ways out of 36 to win, which means there are 24 ways out of 36 to lose. What's the likelihood that I win on my first roll? So probability that x is 1. Well, that's going to be 8/36. Probability that x equals 2, that is that I win on my second roll. That meant my first roll was a failure, and then I had a winning roll. Third roll. First one's a failure. Second one's a failure. Third one's a win. Seeing a pattern? Probability that x equals 4. That my first winning roll is on the fourth roll. 24 out of 36, 24 out of 36, 24 out of 36. Then I have 8 out of 36. Or in essence, the probability that x is on the nth roll will be q, that's an equal, to the n minus x, that's a minus. It's really tiny, but that little symbol right there should be minus, not times. Then times p. So if I want the fourth roll, that means I need 3 failures in a row. So that's how you do a geometric. I'm just going to erase that for now because it's going to mess people up. So I've not. So this will be, sorry, n minus 1. There you go. If it's 4 rolls, it's going to be n minus 1, so 3 failures, then a success. A geometric, expected value of a geometric, 1 over p. Think of a dice. If you want to roll a die until you get a number 3, how many times do you expect to have to roll it until you get a 3? The probability of any one success is 1/6, so you'd expect to have to roll it 6 times, which is 1 over 1/6. Don't worry about the standard deviation of a geometric. I'll show it to you as a formula right here. That's a square root. That's like that. We're not going to spend a lot of time with geometric, but being able to identify, how do I know it's a binomial? How do I know it's a geometric? It's a geometric if instead of having a set number of trials, I'm going to go until I get my first success. That's a geometric. All the other conditions are the same. And we would write it like this. My distribution follows a geometric distribution, or my x variable follows a geometric distribution, and the p is the probability of success. So this is where I was hoping to get to. We have less than a minute to go, so we're not going to get to this one. But it will be on the video. I recommend taking a look at how to do it. I will do my best as soon as class ends today. I'll kind of crank out a solution so that there's a solution to it. With that being said, you're working on those first problems in your Check Your Understanding from our textbook related to binomial and geometric distributions, which are the first 2 sections of chapter 4. See you next time. So what I encourage you to do is actually pause this, take a look at it, and then come back to it. And then I'll start going through the conditions and what we can determine about this. All right, welcome back. So first thing first is you need to figure out, is this a binomial, geometric, or neither? And then regardless of any of them, find the following. So the game involves selecting a card from a regular 52 card deck and tossing a coin. So I got 2 things going on. Coin's a fair coin and equally likely, so that means its probability is 50-50 or 1/2. And it says if the card is a face card and the coin lands heads, you win $6. If the card is a face card and the coin lands tails, you win $2. If the card is not a face card, you lose $2 no matter what the coin shows. So first off, is this a binomial? So you go through what the conditions are for a binomial. Are the probabilities the same every time? So we're going to draw 1 card and flip 1 coin. And since they're independent of each other, then the probability of success is constant and they're independent. Do I have a certain number of trials? It doesn't say that, what's going on in here. They didn't say like, hey, do this 10 times. So I don't have a set number of trials. Also, there's 3 outcomes. Either I win 6, I win 2, or I lose 2. So in that case, since there's 3 outcomes, it cannot be a binomial. To be a geometric, I need to have constant probabilities, which I do. I need to play until I have my first success, which I don't have. And again, with a geometric, it's also 2 outcomes, either success or failure. Here, again, there are 3 outcomes, so it's not a geometric. So this would be neither. And so what's happening is either I'm going to have, so kind of when you're thinking about outcomes, my x, I'll either have, it says a face card, and I'm going to use probability notation, a heads, face card and a, that's not, there we go, and a tails. And then not a face card. And it says heads or tails. So heads or tails. So then we're going to talk the probability of X. What's the probability that I get a face card and heads? Does having a face card and flipping a heads on a coin, are they independent events? Since they are independent events, I can use probability of F times the probability of H. And there are 12 face cards out of 52 cards times a half. So this would be 6 over 52. This would be probability of face card and a tail. Well, that's going to be probability of face card times probability of tail, which is 12 out of 52 for face cards times a half, also 6 out of 52. And the second one is basically, I just want to find the probability of not a face card. So not a face card is going to be 40 out of 52 times probability of a heads or a tails. Well, that's 1, because you flip a coin, it's going to be a head or it's going to be a tails. So then this will be 40 out of 52. And if you look, all of those probabilities should add up to 52 out of 52 because one of those three things will happen. So with that being said, to find the expected value, I then have to remember what is each one worth. This is $6, this is $2, and this is negative $2. So expected value of any probability distribution is the sum of each x times its probability of happening, which means I take each x, $6, and that's times 650 seconds, plus $2, because that's a winning 2, over 650 seconds, and then minus 2 times 40, 50 seconds. And that would give me a sum total of, verify on your own calculator, but it's negative 0.615. All right, so what does that mean? That means in the long run, I expect my average play of the game, so if I were to play this game 100 times, I would expect that I would lose on average 61.5 cents per play. So should I play this game? So again, let's say we did this 100 times. If we played this game 100 times, I would expect to lose $61.50. It's actually 53.84 cents. Not a good thing to do, obviously, if you're going to play it a bunch of times. So should we play this game to win money? The answer is no, because I will be losing money on average per play of the game. Might not be a whole lot per play, right? You're only losing less than $1 per play, but that still means on average over time you're going to lose values. So there you go. That's the end of it. We'll see you next time.